So what we're going to do in this lab is we are going to use a pH probe to see if we can't accurately figure out and determine some things about a variety of different buffers. We're going to look at two different buffers. The first one that we're going to look at is the acetic acid sodium acetate buffer. So we are going to put these two species here together. So the acetic acid here is obviously my acid, and that guy here is my conjugate base. So what we're first going to do is measure out 50 milliliters of 0.1 molar acetic acid, and we're going to pour that into a beaker. And then we are going to mass out approximately 0.5 grams of the sodium acetate and add it to it. And then we're going to use the pH sensor, and we are going to record the pH of the buffer system. So let's take a look at that. By the way, we have exactly 0.50 grams, and then we're going to check out the pH that's here. So let's check that. Alrighty, so the first thing we are going to do here is we are going to check out the pH of a acetic acid solution here. So we're going to take this and we're going to put our 0.1 molar acetic acid solution in there. And because it is an acid, we should see with our pH probe here, take that guy there, give him a cursory little wipe to get some of that water off. It was just sitting in some water. And we're going to put that guy in here, and we're going to check out what the pH is. And sure enough, the pH of this guy goes significantly low because it should, because this guy here is an acid. Now what we are going to do is we are going to take this acid solution, and we are going to add in the conjugate base to it. And right here I've got that half a gram of the sodium acetate, which is there, and so we're going to put that in and stir. And then what we should see here is we should see the pH of this guy rise because we are adding a conjugate base to our acid here. So we're going to go ahead and put this in like so, and we should see at least a little bit. Oh yeah, we're getting some real good rising there in the pH as this guy goes through and dissolves. So the sodium acetate is dissolving. You've got to be very careful. You really probably shouldn't be doing this. I shouldn't be stirring with the probe itself because it's got a little glass bulb at the end, and if you stir it too hard, that glass bulb will break, and you'll end up with a useless pile of circuitry here. So this looks here like I'm topping out at a pH of about 4.1 or so. Yeah, we're just going to go ahead and call that a pH of about 4.1. So the pH of the buffer turned out to be right at 4.1. Now, what I'd like to be able to do is do some calculations with this. First of all, I want to know what the concentration of the acetate is here. This, by the way, again, is my conjugate base in my solution. This guy here is my acid. This guy here is my base. So how do I calculate the molarity? Well, the molarity is just moles per liter. But I had a half a gram of sodium acetate. Now, I don't need the sodium in the overall equation because it's a spectator ion, but I have to include it in the mass because in the solid that I weighed out, the sodium was there. And it was there in the solution all along, it just wasn't doing anything. So it's half a gram of sodium acetate times 1 mole per whatever that stuff weighs. So that's going to be a 32 and 3 and a 24 and another 23, 82. So that's 82 grams there. So half divided by 82 gets us about 0.00610 moles. And that is technically moles of the sodium acetate. But if this is a two-part system, 1 part sodium, 1 part acetate, it's like a unicycle. If I have 61 unicycles, then I have 61 tires and I have 61 frames. So at this point, if I want to, I can go ahead and get rid of the sodium part of things because it's not doing me any good. because I have the equal number of moles of the acetate as I do of the sodium that's there. And all I really care about at this point is my acetate. But if I had not included the 23 grams per mole here in my mass, then that number would have been off, and then that number would have been off, and I would have gotten the wrong value here. So you've got to include those 23 grams per mole that is here, but once it gets dissolved into the solution, it doesn't matter anymore. So now that's moles, and all I have to do, is divide that by 0.050 liters, which is my 50 milliliters. So 0.0061 divided by 0.05 gets me about 0.122 molarity of my conjugate base, which is in the system that's there. So that is my base for the system, and remember, I used 0.1 molarity for my acid that's there. So that's my acid, and that's my base. Now, when we go to do the Henderson-Hasselhoff equation here, remember that's pH is going to be equal to pKa plus the log of the ratio of the base to the acid. Now, what was my pH? I measured that to be 4.1. So my pH is 4.1, my pKa is going to be my X, and then that's going to be the log of the base to the acid. My base was 0.122 and my acid was 0.1 according to the information that I had here. Again, that was my acetic acid. I had 0.1 molarity of it, and then after everything I calculated that my base was 0.122. So slightly more of the base than I had of the acid. So what do we end up with then? We end up with 0.122 divided by 0.1 and then the logification of that. So we end up then with 4.1 is going to be equal to pKa plus 0.0864. So 4.1 minus 0.0864 is going to be about a 4.01 there. So my 4.01 is going to be equal to my pKa. And remember, if you want to know what the Ka is, if you want to undo the P of things, you take 10 to the. So 10 to the negative 4.01 is going to be equal to the Ka. So negative second function log there, scientific notation. So I'm going to end up then with about 9.7 for my Ka times 10 to the negative fifth that's there. And the accepted value is 1.8 times 10 to the negative fifth. So I at least got to the correct exponent of things. So I'm in pretty good shape there. If I wanted to know the percent error, remember that percent error is did minus shoulda over shoulda times 100%. And my number here is actually going to be quite large, but all I really care about is that I got to the correct exponent of things. So this is 9.7 times 10 to the negative fifth minus 1.8 times 10 to the negative fifth divided by 1.8 times 10 to the negative fifth. So that's going to be 9.7 times 10 to the negative fifth minus 1.8 times 10 to the negative fifth divided by 1.8 times 10 to the negative fifth times 100%. It's about a 440% error. But again, all I really care about, when you're starting to talk about exponential things, if you get to the correct exponent there, you are in good shape. Our next one here is trying to prepare a buffer to a particular pH that is there. So what we're going to be doing here is we are going to be doing a sodium bicarbonate and a sodium carbonate buffer. So it says calculate the mass of sodium bicarbonate that will be added to 50 milliliters of 0.1 molar sodium carbonate to produce a buffer with a pH of 10. So what you need to recognize is that this stuff here is your acid and this stuff here is your base. So again, it says Ka of HCO3. So the thing with the H there is your acid, and then the thing over here without the H is going to be your base that is there. So why does that matter? Well, it matters because we're going to do the Henderson-Hasselbalch equation. pH is going to be equal to pKa plus the log of the base to the acid. Now, I want exactly a pH of 10, it says. And my Ka is 4.8 times 10 to the negative 11th. So then that's going to be the negative log of 4.8 times 10 to the negative 11th. And then we're going to add that to the log of the base to the acid that is there. So the base, I know, is going to be 0.1 molar because that's my conjugate base. And what I'm really interested in is how much of my acid I am going to have here. So my acid is going to be my X. I don't know that, but my base is going to be 0.1. So I can go through and do some math on this. So this is still 10. And what's the negative log of 4.8 times 10 to the negative 11th? That's a 10.32. And then that's going to be plus the log of 0.1 over my acid. And so then subtractify that over, and I get negative 0.32 is going to be equal to the log of 0.1 over my acid. How do you undo a log? You take 10 to the, so this is going to be 10 to the negative 0.32 is going to be equal to 0.1 over A. And except that 10 to the 0.32, negative 0.32 is 0.479 is going to be equal to 0.1 over A. And so my acid concentration that I need then is going to end up being 0.1 divided by 0.479, 0.209 molar. Okay, so I need 0.209 molar, except that's not what the question asked. What the question asked was how many grams of the sodium bicarbonate am I going to need? Well, if I have 0.209, and that's in moles per liter of my acid, which is my sodium bicarbonate, all I got to do now is get that to grams. I'm going to multiply that by 0.05 liters because it's 50 milliliters. And that'll get rid of my liters. And then I'm going to multiply that by, what does that stuff weigh? 84, 48, plus 12, plus 23, plus 1, 84. So that's 84 grams per mole. So 84 at 0.05 at 0.209 is about 0.88 grams of baking soda, of the NaHCO3. So theoretically now, if I take 0.88 grams of baking soda and add it to 50 milliliters of my sodium carbonate solution there, I should theoretically be able to get pretty darn close to a pH of 10. Let's check that out and see how we do. Okay, so here's what we got here. We've got 50 milliliters of my 0.1 molar sodium carbonate solution. As soon as I add this in, you're going to see the pH skyrocket because this stuff is basic. So this stuff here is going to go way above a pH of 7. So stir that guy around. So sure enough, we are well above a pH of 7 at this point because that is our base that's there. And what we're going to do now is we're going to add in our baking soda, and our baking soda is going to act as our conjugate acid of the system, and the conjugate acid of the system should bring the pH back down a little bit towards 7 because, again, this is the acid portion of things. So this is your 0.88 grams that we calculated before. So here is my 0.88 grams, and as I stir this guy in, now it's not exact, but it's in the vicinity of a pH of 10 at any rate. I'm getting about a 9.6 there with this, which again, you got to keep in mind you're dealing with logarithmic mathematics at that point. So that's in the ballpark at any rate, and I'm pretty happy with that. I am good enough to go with that. That guy there is pretty darn close to this. All right, now what we're going to do is we're just going to compare the buffering action of things. So what I'm going to do here is I'm just going to take this guy and put him in some water. And if I take this guy and put him in some water here, you can see that its pH will eventually get down to around 7 or so. You know what, I'm not even going to wait for it to acclimate. What I'm going to do is I'm going to go ahead and I'm going to add in some 6 molar hydrochloric acid. And if I add in a few drops of 6 molar hydrochloric acid to this guy, we can see if we swirl this guy around, all that was just a few drops of hydrochloric acid, and boom, this guy plummets down to a pH of around 1 or so, because there's nothing to stop that strong acid from acting like a strong acid. Now, if I were to, instead of doing that, instead use my buffer system that I made here, and remember my buffer system was buffering at around a pH of 9.5 or 10 or so. So wait for that to get back up there. But if I were to do the same thing here with my buffer system and then just add in a few drops of my acid like so, the buffering action of this, nope, not a whole lot of change here in my system, because the weak base that is present turned all of that strong acid into the weak acid. And so I added in a few drops and very little occurred there because of the buffering action. So again, I could add in a bunch more drops like I did, and the pH of this is going down, but it is resisting going down because of the buffering action that is occurring there. So here is, again, a whole bunch more of my 6 molar hydrochloric acid. And every time I add it, the pH is going down, but not nearly like it did in this guy, where it just plummeted straight down to 1 because there was no buffering action in this water that was here. So the whole point of a buffer is that it resists changes to pH. And the same thing occurs if you were to do it with a strong base. If I were to add in some sodium hydroxide here and put in some sodium hydroxide, I could get this pH to shoot right back up by adding in a bunch here of my strong base. But again, there's no buffering action here in this water, and because there's no buffering action, a few squirts of that strong base and it shoots it right back up to the top. But if I were to then put it back into my buffer system that was here, and do the same thing with my strong base, I'm going to add in some sodium hydroxide that's here. If I add in some sodium hydroxide, I am not getting a major change in the pH, because the weak acid that is present is neutralizing the strong base and turning it into a weak base. And so by adding in a little bit of my strong base that is here, I'm really not changing the pH of that very much. Certainly not like pure water was over here, where that just skyrocketed back up. So this is resisting the changes to the pH. It's the whole point of a buffer. A buffer takes the strong species that you add and then converts it to the conjugate weak species of whatever is present, and therefore it resists changes in pH. If you add a base to a buffer, the pH will go up. It just won't skyrocket like it will in water, because there's nothing in water to stop the pH from changing. If you add an acid to a buffer, it will go down, but it just won't skyrocket down, or plummet down, sky plummet down, whatever, ground plummet down, whatever. Mixed metaphors here. It won't change a lot in the process, because in water there's nothing to stop it from going down. In a buffer, there is a weak conjugate system that will take the strong species and turn it into the weak conjugate species, and therefore resist those changes in the pH. The last thing we have here is to write out the net ionic equations for these reactions. All you really got to know for these is you just got to know what species is implied and what it means by net ionic equation. So if you're talking about hydrochloric acid, then it's a strong acid. Then you're talking really about the hydronium ion that is there, H3O positive. We're just going to go ahead and ignore the chloride ion straight up, and we're going to turn that hydrogen ion into the hydronium ion. If you'd prefer to keep it, we can. We can keep it simple. Both ways are acceptable, but the slightly more accurate way of representing it is the hydronium ion, so I'm going to keep that. Keep in mind that in these guys over here, in both of them, the sodium is going to be a spectator ion. So that one has one sodium ion, so he's going to have a -1 charge. That one has two sodium ions, so he's going to have a -2 charge. This guy is your acid. This guy is your conjugate base. So what's going to happen when you add an acid to this system? Well, what do acids like to react with? Acids like to react with bases. And so consequently what you're going to get is you're going to get the H3O positive ion reacting with the base in this buffer system, which is the carbonate ion, to be in equilibrium with water and then the conjugate acid of this, which is that guy like so. If you'd prefer to just use the hydrogen ion, it's not a problem. It's just going to be that, and it's going to come over here, and we're just going to ignore the water aspect of things. Both ways are acceptable. I prefer the top way. In this one here, it says write the net ionic equation between sodium hydroxide and the acetate buffer. Well, okay, fine. So the sodium hydroxide, we're going to get rid of the sodium, which is going to make him a -1 charge. That guy there is clearly your acid. One sodium here is going to give him a -1 charge, and that's your conjugate base. So what is OH? That is the strongest base there is. If I add an OH into these guys, who does a base like to react with? Bases like to react with acids. So consequently, what you're going to get is you're going to get hydroxide reacting with the weak acid that is here to come over here and make water, and the conjugate base, which is that guy over here. So those are the net ionic equations that are typical of being asked in these particular problems. I can just about guarantee you that one of those is going to show up on the AP test.